Okay, so today we're going to be talking about biodiesel versus petrodiesel, and this will be the final installment of our sort of fuels mini series here. And basically, what we're going to discuss today is we're going to be comparing the two different types of diesels that are mentioned in VCE chemistry. We're going to be going in depth with each one of them specifically. And we're going to be comparing them in terms of their utility as a fuel and the environmental considerations when it comes to usage and production of that fuel. Okay, so first off, we're going to start off with an overview of sort of what diesel is. And when we compare diesel to sort of the fuels we discussed earlier in other videos, the utility really comes from its high fuel efficiency. So what that means in essence is if we compared a vehicle going with a tank full of petrol and a tank full of diesel, the diesel vehicle is going to be able to go further on the same amount or same volume of fuel, especially when we compare it to something like petrol or other fuels as well that we've discussed before. So in that same vein, its main sort of user comes from heavy haulage vehicles. So that's sort of heavy machinery, things like excavators, trucks, etc., etc. And so they really utilize this high fuel efficiency to be able to go those long distances or to be able to carry that really heavy load. So going now a bit more deeply into the types of diesel, we have petrodiesel, which from the name you can probably guess it's derived from crude oil or petroleum, so it's a fossil fuel. And it's composed of 75% alkanes, and these are quite long chain alkanes, anywhere from C10 to C15. And it's also composed of 25% aromatic hydrocarbons. And for those who don't know what that means, we're going to talk more about this in Unit 4. But essentially, if you have something like this carbon arrangement here, this is just, I'm just going to draw benzene here. As you can see, these carbons are in a chain or in like a little circle together. And so that's what an aromatic hydrocarbon is. It contains a chain itself in its main chain, or it might have like a side branch as well. And there's an aromatic ring involved with it as well. So that makes up 25% of petrodiesel. Now, if we go down here, we also have biodiesel that I've just introduced now recently. And I talked about this in the previous video that we're going to talk about biodiesel in a separate video. And this is what we call a fatty acid ester. And I'll get a little bit more into what that means when we talk about biodiesel specifically. But it's made through a trans-esterification reaction, which sounds very fancy, but it's pretty straightforward once we knuckle it down into the basic parts. So those are the two different types of diesel. And we're going to compare them a little bit later on when it comes to their efficiencies, their different properties, and their environmental impact. But before I delve into that a bit deeper, I'm just going to make a note that this has a energy content of 48 kilojoules per gram, where this is 41 kilojoules per gram. Just a note on this 48 though, I have also seen 45 as a number thrown around as well in the data book. So it's anywhere from 48 to 45 to 48. So different sources say different things. But the main point is this is still slightly higher than biodiesel. And we're going to talk a little bit about why that is and also sort of the other properties when we compare them as well. But yeah, that's an overview. Okay, so as I mentioned before, biodiesel is produced by a trans-esterification process or reaction. And this is a completely new thing that we've heard in Unit 3 chemistry. And it's not from Year 11 chemistry or anything like that. And it is quite an important part of understanding understanding biodiesel and also understanding sort of how it gets its properties and why we call it a fatty acid ester. So to start us off, I'm just going to write the general equation for a trans-esterification reaction when we're talking about biodiesel. And I'm going to go through each of the components in a little bit more detail. So first we're going to start off with 1 triglyceride. And don't fret if you don't know what that is. We're also going to talk a little bit more about this in Unit 4 when we do food chemistry, but it also comes in here with fuels. Plus 3 alcohol, which produces 1 glycerol. Again, don't worry if you don't know what that is. Plus 3 biodiesel, or the fatty acid esters I was talking about. So with that being said, there's probably a lot of new words here. Let's go through them in detail. So a triglyceride is actually the building blocks of fat. So sort of any sort of fat that we have, from animal fat, plant fat, vegetable oil, etc., it's composed of these triglycerides. And essentially what a triglyceride is, it's 3 fatty acid chains. So let me just draw this out like this. It's 3 fatty acid chains combined to this sort of carbon backbone over here with an ester linkage. So let me just draw that out for you. So if we have, this is our ester linkage, and we might have something like C10H22, right? So that would be like a pentane chain. You might also have, you can have a triglyceride where all the chains are the same length, but you may also have a triglyceride in which you have differing chains. So you might have 2 that are C10H22, but you might have one that's C12H24. So there might be a double bond in there. And you go more into sort of the utility of the different types of triglycerides, unsaturated versus saturated, in Unit 4. But when we mention sort of the comparison between different types of biodiesel, the saturation of these triglycerides will come into play. And just for those who are unaware, a saturated hydrocarbon is one that has no double bonds, meaning all the carbons are bonded to a hydrogen, like as many as they can be, whereas unsaturated is essentially something that isn't that, which means it has greater than or equal to 1 double bond. And this sort of nomenclature comes more handy in Unit 4, as I said before, when we talk a little bit more about the properties of that. Now, this alcohol is usually methanol or ethanol. It can be others, but 99% of the time it will be most likely methanol, but sometimes ethanol. And so for this reason, sometimes these are also called methyl fatty acid esters, because of that meth group that comes about. We just add the hydrogens. So hydrogens would be here as part of this carbon backbone. And when we react, what happens is this alcohol, so if we have like OHCH3, so methanol, for example, it acts on this ester linkage and it breaks it. So instead of having this connected carbon backbone, ester linkage, and chain, what happens is this is broken. So we end up with the methyl ester in this case, where we're using this. So you'll have the methyl ester, so you'll have CH3 OCO, and then you'll have the rest, C10H22. So just to draw that out, it would be like this. This would be H's, and then you would have the C10H22. So that would just be like pentane, a decane, but just really all the way out there. And I think you might not be able to see that, so let me just bring that a little bit closer. So yeah, this would be C10H22. This would be C10H22. So that's the sort of how that would end up working out. And this remaining carbon side chain would turn into glycerol. So if we just bring this down here, which is just sort of, this is kind of the structure of glycerol. And this becomes very important again in Unit 4. So don't think this is just for fuels, but glycerol is also a very important compound in organic chemistry when it comes to food chemistry as well, because of the because of how it works with triglycerides and how it's derived from them. So that's sort of the transesterification reaction. There's one final aspect that we need to talk about, and that is the catalyst, which is going to always be potassium hydroxide. This is just the sort of the catalyst that's always used, and it's the catalyst that works the best. And it just speeds up this reaction and allows it to occur at a very good rate for us when we're talking about the industrial production of biodiesel. The final sort of aspect when it comes to these transesterification reactions and producing this biodiesel is that if you have a saturated hydrocarbon, it's just going to be in a straight chain. So if we just compare this like this, it's just going to be a straight chain, and that's just going to keep going on and on and on until the end of the hydrocarbon chain. Or if this is going to be the end, this would end up being the ester linkage, and then connected to methyl group or something like that. But if you have an unsaturated, fatty acid or an unsaturated triglyceride, I should say, what will happen is at some point along this chain, you're going to have that double bond, and that's going to cause a bit of a kink in the chain. And this kink affects the dispersion forces. So obviously, if we were looking at, so if this is, for diagrammatic purposes, like a straight line, and this is more of like this sort of, I guess, staircase shape, you could call it. If we're trying to have like if this is a compound, a mixture, and there's lots of these little staircase shaped sort of things wandering around, it's going to be very difficult for them to pack together like nicely. Whereas, you can have these flat lines sort of on top of each other, and it would be perfectly fine. So these unsaturated fatty acids have weaker dispersion forces, and as a result of weaker dispersion forces, they have just like weaker intermolecular bonds in general, and so they have lower boiling points, lower melting points, things like that, and that also affects things like viscosity and other sorts of chemical properties that are influenced by these intermolecular bonds.